So we have data, and we want to determine if it's linear, exponential, or neither. So it's a good practice to see what kind of data we have. I'm going to show you a few different ways, and it's up to you to decide what you like for showing it. Now the first thing, if you notice this first table, first thing we should notice, the inputs are equally spaced. So that means if we want to check for linear, we just need to check the differences, and this is only because the inputs are equally spaced. Because if we were doing slope, we'd be dividing by the same number every time. So this one, the difference is 3.2. This one, the difference is 3.2, 3.2, and a difference of 3.2. So this first one is clearly linear. Now, if the inputs had not been equally spaced, we would have done this 16.4 minus 13.2 divided by 2 minus 1. So we would have done the slope for each pair. If they had not come out linear and the inputs were equally spaced, we would just divide successive outputs. So we do this one over this one, this one over this one, this one over this one, this one over this one to check for exponential. And we kind of go that way. We check linear first. If it's not linear, then we check exponential. If it's not exponential, it's neither. Let's go to our next table. Notice our inputs this time are not equally spaced. So we can't just do the differences, but we could look at the slopes. So the slope here on this first one, we have 6 minus 3 over 2 minus 0. So that's 3 halves. Here we have a difference of 6, change in output over a difference of 4. That's 3 halves. Here we've got 12 over 4, which is 3, so it's definitely not linear. So the next thing we need to check is exponential. And what we would do to check exponential is we have to check successive outputs. So for instance, we would do 6 over 3, but we also have to take into account the distance in the inputs, because this would be like saying our base squared is 6 over 3. This would be like saying our base to the fourth is 12 over 6. And we may have enough information here because right here b squared ends up being 2. Again, these numbers, this is where the 4 came from, this is where the 2 came from. If we needed to check this one, we also have a 4. We do b to the 6th is 48 over 24. So to check all of these, I'm just checking a couple right now for time's sake. And here we end up with b to the 4th equals 2. There's no value of b that's going to work for both of these, so this is also not exponential. That b should be the same for every single one. So let's just set up the other two that we would need to test. We'd have b to the 4th equals, so that from this pair here, 24 over 12. And here we'd have b to the 6th equals 48 over 24. Now notice all of these divide out to be 2. So it's really tempting to say that it's exponential. And if the inputs had been equally spaced, it would have been. Since they're not, it's neither linear or exponential, so it's neither. Let me show you one last option for the last one here using the calculator. We can do it with our regression. So if you go to your stat edit and put in your data, your x's and your y's, you can now quit out of this and you can do both your regressions. So we can do stat calc linear regression. We should get a correlation coefficient of 1. If your correlation coefficient is not on, which mine is not, this is good practice actually, you can go to, you need to turn on your diagnostic, so go second catalog, and you want to go all the way down to the D's, and you're going to see a thing called diagnostics on and off, so let's turn them on. And so now when I run my linear regression, there's my correlation coefficient. It's pretty close to 1. But we should be seeing 0.99999 if the data is truly linear. Let's compare it to our exponential regression. So we'll quit out of here, and we'll go to stat calc exponential regression. Look at that. We got a correlation coefficient of exactly 1, negative 1 because it's decreasing. So this data is in fact exponential, and that's how you can check it with your calculator using regression.